Hi, I'm Adelina, and together with Rebecca and Subin, we'll be talking about Augustin-louis Cauchy and what he did to be considered one of the most influential mathematicians of modern times. But first, a bit about the life of the man himself.
Augustin-louis Cauchy was born in Paris on the 21st of August 1789, 10 days after the fall of Bastille and the start of the French Revolution, to middle-class parents, Louis-François and Marie-Madeleine. Cauchy's father was a parliamentary lawyer, lieutenant of police, and an avid royalist. Sensing danger with the fall of Bastille, Cauchy's father decided to move the family to a town called Arcueil in the French countryside. It was there that Cauchy received a highly religious education from his mother and a classical education from his father until the family moved back to Paris when he was 11 years old. The French Revolution lasted for the first 10 years of Cauchy's life. By the year 1800, the French political situation had settled, and Cauchy's family felt safe enough to move back to Paris, where at the age of 18 he entered École Polytechnique, which at the time was considered one of the best schools in the world for young aspiring mathematicians. The teaching at the school was linked with research being conducted with the nation's leading mathematicians, and Cauchy attended courses by Lacroix, de Prony, Hachette, and his analysis tutor was Ampere. As well as attending this highly prestigious school, Cauchy's early life was influenced by the mathematicians Laplace and Lagrange, who were frequent visitors to his household. These famous mathematicians were highly influential at the time, and Lagrange in particular took a deep interest in Cauchy's mathematics education. As Laplace and Lagrange had predicted, Cauchy excelled at his mathematics school, and after graduating from the École Polytechnique in 1807, he entered the engineering school École des Ponts et Chaussées. After graduating, Cauchy became an engineer in Cherbourg, working on port facilities for Napoleon's English invasion fleet. While he was working as an engineer, he couldn't resist also conducting mathematical research and started proving theories about polyhedrons, symmetric functions, and determinants. Cauchy eventually decided to stop his work as an engineer and focus on his mathematical research after a bout of depression in 1812, where he decided to return to Paris. This decision proved extremely fruitful for Cauchy as he became a prolific research mathematician with a plethora of awards and titles. By 1818, he was married to his wife, Aloïse de Burgh. He then had two daughters, Marie-Françoise Alicia in 1819 and Marie-Mathilde in 1823. Throughout his life, Cauchy baffled his contemporaries with his staunch evangelical Catholic faith. They could not believe that such a brilliant academic mind could hold such bigoted views when it came to religion. The Second French Revolution in 1830 sent King Charles X into exile, and the new king Louis Philippe demanding oaths of allegiance from French professors. Cauchy refused, having already sworn his allegiance to Charles, and was stripped of his honours. He then exiled himself to Switzerland, leaving his family in Paris. He was later allowed to return to Paris, where he worked as a lecturer. Cauchy died on the 23rd of May, 1857. His last words are believed to be, "Men die, but their works endure."
Next, I'll talk about Cauchy's mathematical accomplishments. It's very unlikely you've never heard the name Cauchy before, given he has formulas named after him in everything from number theory to elasticity, algebra to hydrodynamics. His contributions to math and science certainly haven't gone unnoticed. However, it was his contributions to the development of calculus in his publication, Cours d'analyse, that he truly made his mark. While calculus had existed for over a century prior to Cauchy's birth, its foundations were still somewhat weak. Cauchy was one of the first people to help construct a more rigorous foundation that logically explained calculus. Cauchy is considered the first to define calculus in terms of limits and continuity, and also introduced the epsilon-delta notation used in calculus proofs and definitions today. A big contribution was his criterion for convergence. A Cauchy sequence is a sequence an where for all epsilon greater than 0, there exists a positive integer n, such that for all n and m greater than n, an minus am is less than epsilon. Since every convergent sequence is Cauchy, it provides a method of determining convergence without a limit. Cauchy is also considered by many to be the father of complex analysis. While the idea of complex numbers definitely didn't originate with Cauchy, he provided the first comprehensive theory of complex numbers, forming the foundations of the field. Most famously is his integral formula, where if f of z is an analytic function for a simply connected region in a complex plane, and if c is a closed contour in the region, then the contour integral f of z dz equals 0. When generalized, you get the residue theorem, 1 over 2 pi I times the contour integral of f of z dz equals the sum of the residues of f of z. This allows us to evaluate line integrals of analytic functions over closed curves.
I have researched about Cauchy's work with other mathematicians. One of the famous work is Integral Test for Convergence. This work is combined with Maclaurin, so it is called Maclaurin-Cauchy test as well. Most of the students must have learned this test in first year in University of Mathematics. This is when let the function f be continuous, non-negative, and monotone decreasing function, which is bounded from n to infinity, where n is a positive integer. Then the finite series an will converge if and only if the integral of the function from 1 to infinity converges. So conversely, if the integral of the function diverges, then the series diverges as well. Thanks to this discovery, we were able to find some harmonic series, such as 1 over n series, where n starts from 1 up to infinity diverges. This is an important discovery because the proof gives the lower and upper bound for finite series if the improper integral is finite. Another great contribution is Cauchy-Riemann equation. This discovery is used in complex analysis, which consists two partial differential equations, which are du over dx equals dv over dy, and du over dy equals negative dv over dx. In complex fields, u is a real part and v is an imaginary part which consist x and y. In order for the equation to work, both of the functions u and v should be continuous and differentiable. This is a condition for complex functions to be holomorphic, in other words, to be complex differentiable. This work has first noticed by D'Alembert in 1752, and Euler has connected this to analytic functions later in 1797. Then Cauchy used this equation to construct his theory about functions in 1814. Riemann wrote this equation in his thesis in 1851. It became Cauchy-Riemann equation. We still use this test, shortened as CRE, in complex analysis to determine whether the complex field is holomorphic or not. In conclusion, Cauchy has contributed a lot of work in mathematics, and he has developed a lot of expansion in many aspects of mathematics. Thank you for listening.